Hello again. Today here in physics class, we're going to be talking about situations of equilibrium. Equilibrium can mean a lot of things in everyday English, but in physics it's very simple. It means that the sum of all the forces on an object is zero. If that's true, then the object is in equilibrium. But what does it mean to say that the sum of the forces is zero? What are the consequences of that? Well, very simply, it means that the acceleration is also zero. Now, in most equilibrium situations, we're going to talk about things that not only have an acceleration of zero, but also aren't going anywhere, at least not relative to their surroundings, like a bridge or something that you'd like to stay in the same place. It's always nice when you're driving along the highway that the bridge you expect over the river is actually there when you get to it. Or we do want the velocity to be zero. So in that situation, the particular branch of physics we're talking about is called statics. In college, if you go into engineering, you'll probably take a class called statics, or maybe a class called statics and dynamics. Statics are for things that are not moving, and dynamics are for things that are. Kind of makes sense, doesn't it? The fundamental ideas surrounding this are the definition that the sum of the forces is zero. Note the vector symbol. That isn't necessarily how we do the problems, although it might be. Typically, what we do is we break things into their components. And so that means that the sum of the forces in the x direction are zero and the sum of the forces in the y direction are zero. So it's not accelerating in any direction. And of course, out here in the real world, not in physics problems land, it would also be the sum of the forces in the z direction is zero in any direction that you pick. So there's no force. Got it? All right. So let's take a look at a quick example. 150 kilogram traffic signal. We need a picture of this thing. There it is hanging from two wires. If the wire on the left makes a 21-degree angle to the horizontal and the wire on the right makes a 32-degree angle, what is the tension in each wire? There's the angle on the left, and there's the angle on the right. Now, I hope it's immediately obvious to everyone who's thinking about it that this is an important question. Traffic signals are much bigger than you might think they are if you ever see one up close and at eye level instead of hanging way above you. They're heavy, and it'd really be nice if the wires that are holding them up are actually strong enough to hold up that amount of tension. So we need to be able to compute that just for safety purposes and just to be able to get the job done. So this stuff really, really does matter. Now, how are we going to do it? Why, that's right. We're going to be drawing a free body diagram. But a free body diagram of what? The traffic signal? The wires? The thing up above the wires? It's so hard to say. Well, we're going to draw our picture, our free body diagram, of this connection right here, because that's where all the forces meet. The tension in this wire pulling in that direction, the tension in this wire pulling in that direction. By the way, tension, again, always means a pulling force, and you can't really push a wire. You have to pull it. You can't push a string. You have to pull on it. And of course, there's tension in this wire pulling down this way. That's where all the forces meet. So this is what we're going to be drawing our free body diagram for. Since it's in equilibrium, we don't have to worry about the mass because there isn't going to be any acceleration to deal with. Of course, the connecting point doesn't have any mass. The traffic signal does, and that's what's providing a force, but it's the force that matters. So let's draw that free body diagram. It's going to look like this. They are all pulling forces. Can you see that? We'll call the force on the wire on the left tension 1. The wire on the right we'll call tension 2. Tension 3 will be the weight. Weight, of course, is calculated by mg. Since it's a 150 kilogram traffic signal, we multiply that by 9.8. 150 times 9.8. And sure enough, we get 1,470 newtons. Okay? We need to put other information in there as well, such as the angles. So we have 21 degrees and 32 degrees. Now, what do we do to analyze this situation and come up with how much tension are in those wires? Well, one approach is to use what we call the component method. The component method says that the sum of the forces in the x direction is zero and the sum of the forces in the y direction is zero. Well, here's the problem. I haven't established an x direction or a y direction. So let's choose some positive directions right now. X will be to the right, Y will be up, which means negative x is to the left and negative y is down. Okay, so this force, if I break it into components, will have an x component like this, and we can call that t sub 2x, and it'll have a y component like this. Whoa, that was quite a curve. And we'll call this t sub 2y, and those can be computed pretty easily. This force will have an x component to the left, t sub 1x, and a y component, again up, t sub 1y. I want you to notice something. Does it make good sense that if this is an equilibrium, all the x components, namely this and this, will cancel, and all the y components, namely this and this, which are positive, and this, which is negative, will cancel? Absolutely. And so what we're looking at is we're looking at saying that the sum of these two forces is 0. That we get from this equation. And the sum of these three forces is 0, which is what we get from this equation. And so let's compute them. Let's start with the x direction, and we'll do this right up here. T1x is in the negative direction. If I use this acute angle of 21 degrees right here, instead of starting at 0 and coming all the way around to 159 degrees, as long as I toss in the minus sign, it'll work just fine. So I can write negative T1 times the cosine of 21 degrees. Why cosine? Cosine is adjacent over hypotenuse. I have the hypotenuse. I want the adjacent. Okay. That'll give us this component. That's T1x right there with the appropriate minus sign. Plus T2x, which is going to be T2 again times the cosine, but this time of 32 degrees. Now what's the sum of all of those forces? Yep, 0. And I think at this point I need to mention that whenever you have an angle in degrees, always put the little circle up there. I know it seems pointless, but if there's no little circle up there, it actually is kind of implying that you're working in radians, which we most definitely are not in this situation. So let's do the same thing in the y direction. T1y, let's see, that's a positive force. Note the arrowhead. Note the positive y direction is right up here. And so that's going to be T1 times the sine of 21 degrees plus, what's this one going to be? If you want to, you can pause the video and try it on your own. I will tell you what it is, however. It's going to be T2 times the sine of 32 degrees. Sine has an n, 32 degrees, is equal to, oh, wait, is not equal to, those aren't the only forces in the vertical direction. Oh, what have I forgotten? Oh, I've forgotten about T3. That's right. And it's a negative force. So let's write minus 1470. And that's the sum of all the forces in the y direction. And that's equal to 0. Now, let's see what this means when we actually use the calculator to compute the cosine of 21 degrees and so on. Well, we can rewrite this problem as follows. Ta-da! There they are. The cosine of 21 degrees is 0.9335. The cosine of 32 degrees is 0.8480, and so on. Notice that I moved the 1470 over to the other side as a positive. In other words, I added 1470 to both sides. And so we have a little system of equations that you need to try to be able to solve. If you don't remember how to do that, please return to your Algebra 2 instructor and ask for some help on this. But if you solve it correctly, you get that T1 is equal to 1,560 newtons. And T2 is equal to 1,720 newtons, which means your cables need to be able to support at least that much. In fact, actually your cables need to be able to support far more than that, because who knows how much stress would be put on them by some wind. But if they can support only that amount or less, there's a really good chance that they're going to snap. Okay, so not only have we done some physics, we've done a little engineering, and I think we should feel good about that. Now, that's not the only way to solve this problem. Let me show you an alternate method. If we set up the same problem, same forces, same angles, but this time we use something called the triangle method, I think you'll like this. The problem with this method that I'm about to show you is that you can only use it if you have 3 forces in equilibrium. Not 2 forces, not 5 forces, 3. But if you have 3 forces in equilibrium, this will work. The idea behind it is twofold. First, we know that the sum of the forces has to be 0. And second, we know that on a force diagram, when you add the forces arrowhead to endpoint, if the total sum of the forces is 0, that means there's no resultant vector to draw after you add the 3 forces. That is, the final force comes back and touches the tail of the first force. Let me show you what I mean. If I draw a picture of these forces as we would add them, note you don't add them like this. That's tail to tail. We do arrowhead to endpoint. So if I do them this way, here's T3, which is 1470. And then arrowhead to endpoint, let me tack on T2 here. It's going to look like this. Here's T2. Notice it's not a component, it's the actual T2, with an angle right here of 32 degrees. And then I add T1 to T2. That's going to come up like this. Here's T1. And if I draw a little horizontal here, this angle right here is 21 degrees. But a little geometry fact, remember alternate interior angles? That means this angle right here is also 21 degrees, right? And then this one is vertical. Notice it comes back to where it started. If the object's in equilibrium, or the system is in equilibrium, that might be a better way to say it, this is what the 3 forces, if there are exactly 3 forces, would look like. They have to come back around to where they started, because now if I try to draw the shortcut from where I start to where I finish, I'm at the same place. My net force is 0. So then how do we do this problem? Well, if this is 32 degrees here, then this is 32, this is 21, which means the actual angle between these 2 forces is 53 degrees. That makes sense? Furthermore, since this is vertical and this is horizontal, this angle here is going to be 90 minus 21, which is 69 degrees. And since this is 90 degrees from vertical to horizontal, this angle in here of the triangle is 90 minus 32, which is 58 degrees. How does that help us? I'll bet I see some people who know how to do this. We use the law of sines. Remember the law of sines? It says the sine of angle A over side A is equal to the sine of angle B over side B. But the law of sines only works for triangles. If these were 4 forces, you couldn't use the law of sines. In fact, I don't know of any law that you could use other than breaking it down into components anyway, or doing some serious work with trigonometry. So let me show you what I mean. Let's say we want to write T1. Then we could write that the sine of 58 degrees over T1 is equal to, now we pick 2 things that we know. So we write the sine of 53 degrees over 1,470. Got that? Sine of 58 over T1 equals sine of 53 over 1470. Go ahead and solve that, and then see if you can write a similar law of sines equation to find T2 and solve that. Pause the video while you're doing all that, and then come back and we'll take a look at it. Okay, you back? Here's the equation you might use to find T2. The angle opposite T2 is 69 degrees, so we can write that the sine of 69 degrees over T2 is equal to the sine of 53 degrees over 1470. And then it's just a matter of setting up and solving proportions. If you work this first proportion correctly, you should have that T1 is equal to, well, I got 1,560 newtons. And over here, I got that T2 is 1,720 newtons. I rounded both of those to 3 significant figures. Those look familiar. Why, they're the same answers we got when we did the problem by the component method. Which method do you think is easier? That's up to you. I will tell you this. This method will work only if you have exactly 3 forces and they are in equilibrium, so it'll form a triangle. The component method that we saw earlier will work no matter how many forces you have. It'll work all the time. It's a little trickier trigonometrically, but like I said, it always works. So you need to learn both. All right, we'll do another equilibrium example in the next video. I'll bet you can't wait for that. See you later.